I don't know what it is about Thursdays, but we always have lower in-person turnout. Must be whatever else is going on. Who knows?
Oh, it's hard to wake up on Thursdays.
Well, I'm a morning person, so yeah. In the winter, it's just bad for me because when the sun goes down, I want to go to bed, and when the sun goes down at 4:30, that's a bit problematic. Yeah. It's weird because I have no problem getting up when it's dark, but I can't stay up. So.
Tuesday, I had no problem. Today was a little harder because the sun wasn't.
Yeah. Well, definitely, I know when we have winters where there's gray for weeks at a time, I really have trouble with that. Where the blinding snow and stuff. I mean, people don't like that, but actually for me, as long as it's sun, that's the most important thing, and not too windy is the next most important thing. All right. Yeah, so this looks like we are started here, and cool. So today. Oh, okay. Cool. Okay. Well, I'll wait just a minute or two. Good morning. Some more cold drinks. See, I can tell it's spring.
Yeah, that was a long line.
Good. Well, you pay for that extra work.
So I actually have a quick question.
Sure.
Now we're technically allowed to purchase the course packet or whatever off the bookstore.
Yeah.
I don't think they've had it in stock for the whole semester.
Oh, funny.
Yeah, so, I mean, I've just been printing it out myself, but do you know if it's ever going to be back in stock?
I don't know. I could ask her. It might have just been, I used to not provide this stuff online because there are copyright issues, but now that we have a protected way of signing in and getting the stuff, everybody's already paid for the copyright because, as long as you're a student, you've paid through the library and stuff. They have access to all this stuff. And so, anyway, that totally undermined their business, of course, because it's a third party. It's trying to make a living printing these things. And so maybe they sort of gave up on me.
Possibly.
Yeah, maybe I should stop saying it's available. Another way to do it is I could make it available through the ECE department, but their printing costs are high. So, on the other hand, we wouldn't have the copyright costs. So it might actually turn out okay. I don't know.
I was just considering getting it because I've been using up a lot of paper printing everything out and a lot of ink.
Well, I think I still have some extra copies. I don't know, but
I mean, it's not a big deal. I mean, if anything, I could just put it on my iPad.
I like paper too. I like reading off paper. Turns out it's a lot higher resolution than my Retina display or whatever they make nowadays.
It's nicer for highlighting as well and actually like taking notes.
Yep. Well, and as you can tell, some of the readings I couldn't find the original, so I just copied what I had, which is already had scribbles on it. I tried to erase anything that was embarrassing, and
it's still legible though.
Yeah.
All that matters.
All right. Well, let's go ahead and get started. Homework 4 is due on Tuesday. Homework 4 I especially like. It's an AI paper, an AI method. It's programmed rules, so it's not what's popular now, the deep learning stuff. In a sense, there's less magic in it, which makes it less to the liking of many AI people. The programmed rules are understood, but it's interesting because usually rule-based systems actually don't work. They're not expandable. People say they work, but I've been in academia long enough that it's actually very hard to make a rule-based system where the rules don't just conflict and fight it out. So, for instance, for music printing, you can get big books that will tell you this is how you print music. This is how music is engraved. And they'll show you, in this situation, you do this. And then on the next page, they'll show you an exception, and then another exception, and another exception. And, when this happens, you always do this. But then actually, if you look somewhere else in the thing, oh, no, well, if this other thing happens, then you don't do that. And so it's very, very hard to make a rule-based system out of information like that, because a human looks at it and figures it out. But it's hard to encode that. This paper is especially interesting because of the hundreds of papers like this. This one actually works and does some very smart things. One of the things is it does global processing. This paper, it looks at the overall piece of music. And if there's an exception somewhere in the music, that doesn't trip it up as long as generally it's true. For instance, if it's trying to figure out what's the time signature, or what are the important, what are the strong beats, like what are the downbeats of each bar. And that's unusual. Most of these techniques, you sort of have blinders on. They're looking at a very small part of the music. Well, this works well because it does a lot of global processing. You will see that over and over and over again in this class. That, well, even last lecture, I was talking about when you look at the pitch of a note. If you want to do a Fourier transform and you just take the first peak in the Fourier transform and say, oh, that's my fundamental, you're going to have a lot of trouble. There's a lot of peaks in that spectrum. You're way better off looking at all the peaks in the spectrum and somehow trying to combine that information. And we'll have a pitch detection lecture on that, but the global thing is way better than looking at a single peak. Even if that single peak was the fundamental, you're still getting a lot of error because you're just looking at one data point or maybe a few data points right there. You're ignoring all the other data. Where if you look at all the peaks together, then you'll get a much better idea of what pitch is, much more accurate, that sort of thing. Actually, for that, in this particular spectrum here, which I'll talk about in a second, the fundamental is even missing. So if you take the first peak, you'll have one of the harmonics. You won't even have the fundamental. So global processing is good. You want to look at all of it. And same thing is true if you're trying to understand music. If you look at the whole piece of music, and generally, then you can transcribe it better. A human does that too. Now, even if a human were transcribing real time, because of familiarity with styles of music and because of all sorts of musical training, they're actually listening to a lot more than just the note that's in front of them. There's a lot more going on there. And the second part I had up there is use of AI approach, easy to understand and compatible rules. This is a big deal. Like when you look at the rules in this paper, if you read this paper, you might think, wow, well, AI isn't that hard. You just sort of write down intuitive rules for what it's supposed to do, and it does it. No, that usually doesn't work out very well. And this paper is quite unique in the sense that it has rules that are based on, are sort of fundamental music theory related things, and they all get along with each other. The rules don't collide and give you bad results. So that's really cool. And the other thing that's, again, for this holistic thing, local versus global, there's another kind of look at the whole picture. And that's, in this case, combining rhythm and pitch analysis at the same time. And of course, a human does that. You're listening to a whole piece of music. If you're going to notate it and, you have a passing tone or something, you can tell from a lot of different things, including rhythm. And it turns out that normally when music is transcribed, that's just ignored. People have something that tries to figure out the pitches and something else that tries to figure out the rhythms, and they're not intertwined. So anyway, I'm quite impressed with this paper. It's no longer a new paper anymore, but it's really an impressive example, because you'll see a lot of papers written by AI people where they just want to show, look at all these applications I have for my thing, but actually it doesn't work for a very large variety of things. It's not expensive. They say, oh, we just add some more rules and then it does it. And that's actually a falsity. And then there's also the kinds of papers you read from signal processing people where their main goal is to develop new signal processing methods because they're signal processing researchers. And actually sometimes a new approach using old-time signal processing that's been around forever is the most effective. And so you see this happen a lot where sometimes something simple does work, but it's hard to get anything to work, and then it's very hard with all the stuff that's been published to try to figure out, well, what out of all of this, do I actually believe or actually will work in any practical situation? Anyway, so I like this paper because this is one that I found to be quite impressive, delivers what it appears to deliver. Okay. So yeah, I hope you enjoy the paper. If you don't know any music theory, like if you don't know what the circle of fifths is, please start on it early, and please don't expect somebody to be able to in 3 sentences tell you what, it's as if you didn't take ECE402 or 210 or any programming class, and somebody asks you, oh, so how do I program this algorithm? And they want to do I don't know what. If they've never programmed before, you can't explain that in 3 sentences. You can give them some general idea. Anyway, be aware you've got that problem with music theory. Like engineers don't mean to, but there's this sort of weird, almost condescending thing that people inadvertently do, which is, oh, well, it's just music. Somebody can tell me what this is, I commonly get emails say, oh, what page on the internet can I read to learn this? There's some truth to that. In this paper, if you ask if you take your time with it and start early enough, you can, fill in your gaps. But just be careful about just assuming that music majors actually don't do anything all day. Because that's what's implied when you think that, oh, you don't need to take any other courses and you know all your music theory. And this is very basic music theory. I don't mean to scare anybody. If you look at it and you've taken, you've been in band or orchestra or private lessons of any sort, you will know this stuff anyway. But yeah, take your time. If you really don't have the background, your lab partner might know more stuff. You can work with them. You can ask people. Find a music major. Actually talk to somebody that does this stuff. And it'll sort of be fun for them. Those super smart, hardworking engineers. It's sort of fun to be able to tell them really basic things that everybody should know. So just find somebody to talk to. Okay. So that was that. Okay, so we're back here now to our most immediate thing here is we're going to talk about pitch, or the perceived pitch again. We're doing sort of the psychoacoustic idea of pitch, which is a human perception thing, and non-periodic waveforms. I've mentioned this several times that, like, for instance, with the Hammond organ, right? It's easy to make non-periodic waveforms on the Hammond organ. Why? Because a bunch of the partials are not on multiples of the fundamental. They're on the equal tempered scale. They're sort of close, but they're not actually multiples of the fundamental. So if you look at it in a scope, the waveform's always changing because those partials don't repeat an integer number of times within the fundamental period. So here we have another example here, non-periodic pitch sounds. This is acoustic example. Unfortunately, my picture isn't very good. I got to find a better picture. I want to talk about stretched harmonics and for struck non-ideal strings and stretch tuning. So there's several things going on here, but the first thing I want to say is, look, pitch isn't always the same as the fundamental. And why is that? Well, in many sounds, it's true that they're quasi-harmonic. I mean, they're close. Every partial that has any energy worth noting is near an integer multiple of the fundamental. In nature, they're never exact. In synthesizers, they're usually exact multiples. But, they're close enough. And that's cool. So that's, that happens. But there's also lots of sounds in acoustic instruments that where the fundamental is not the pitch you hear. Now, in the Hammond organ, it tends to be, you still hear that fundamental. So, but the pitch you hear, for instance, in a low piano note. Let's, just for example here, let's pretend this is a low C on a piano, the lowest C, which is way down there. You can still, at the lowest C, hear a clear pitch on a piano that's well-tuned, usually. But as you go lower, there's a couple more notes below that. As you get down to the very lowest A, boy, it's hard to tell. That's why they quit there. Because, at some point, if you can't hear the pitch anywhere, well, what's the point? But say you have the C here. Uh-oh. Okay. Say you have the C here, a low C here. Now, what I numbered these things on here, and I apologize for the crummy hand-drawn graph. But anyway, so it's 1 times, 2 times, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times the frequency. But if you play a loud low C on a piano, you'll note, hey, the harmonics keep getting sharper. And the effect is more noticeable as you get higher and higher. Right? They're not multiples of the fundamental. They start out pretty close to multiples. Actually, they start out really quiet, too. It's almost no energy down there. So this is a weird sound for 2 reasons. One of them is there is no energy at the fundamental. Why is that? Well, if you think about what is a wavelength of a low C like that, I don't know, it's around 30 hertz. What is a wavelength? It's huge, right? And a big pipe organ will have, pipes are multiple stories high to do this. But a piano, you want to fit a grand piano into a reasonable sized room. So what they have is they have wound strings. They don't actually have strings that are half a wavelength long, because that would be way too big. Instead, they have other tricks to add mass to the string and make it vibrate at a very low frequency despite its short length. An ideal string has no mass. Okay, all the stuff you learn in physics about harmonics of strings and stuff, an ideal string has no mass. So a low piano string has lots of mass. And the reason they did that is a practical thing. It's just going to be too big an instrument. You don't want an instrument where you have to build a special house for it. A grand piano would have to be, about from where I'm sitting to the back wall of this room. And that's just too big. Nobody wants that in their house, or can fit it in their house, or get it through the front door, or any of that. So they added lots of mass to the strings. They wound the strings. And let's say you're playing a low C here. What that does is, first of all, you don't hear the fundamental much. There's not even a resonance area, to resonate within the piano that's that big. So there's just not going to be much fundamental. Again, if you were to hear the fundamental, you would feel it too. At 30 hertz, you can feel that. You can feel a 30 times per second vibration in your chest, and that's why in a big pipe organ, you would feel that low C. It wouldn't just be something you hear. But your hearing all the same hears it because it puts together all this information from all the harmonics. Now, these harmonics are weird because they go sharper and sharper. Why is that? Well, an ideal string has no mass. So when you hit it, it vibrates nicely. But if you have a really heavy string like that, what happens is, the shortest distance between 2 points is a straight line. And the fundamental has to actually stretch that string, right, in order to make it vibrate to the side. It's no longer a straight line. It has to be longer. So the string actually has to stretch. An ideal string has no problem because it's got no mass. It's got no, it's easy to do anything when you got no mass. So that's great. But the higher the harmonics go, the more the stretch you need for that harmonic, right? It's wiggling a lot more for the same amplitude. And the more it's going to want to return to zero, the less it likes to stretch. But as it tries to return to the steady state, if it returns to the steady state faster, well, that's why the pitch goes up. And you hear that in struck strings, it's a standard issue. So like in the piano here, you play this low note, and by the time you get, say, to the 12th harmonic here, say that you played the low C. I didn't use the low A, which is a very low note, because that really is hard to hear sometimes. And I wanted to make the statement, you can definitely hear a pitch. So let's go with low C. You have the low C. Now, 3.5 octaves up at the 12 times, you'd expect that to be a G. But what happens is it's way sharp because of this effect I was talking about. And in fact, as you go up more octaves, they get even more sharp. That G there, that's by middle C. That's not a particularly high note. Certainly, the core of the range of the piano goes up several octaves from that. The mid range of the piano. So it's quite sharp already there, that G. So what do? I mean, it's a mess if you wanted to play that low C and that G together. Right? They would sound nasty together if you didn't do something about this. Because the low G is making a quite strong amount of energy, but it's not. It doesn't correspond, right? You really want it to be the same as the high as the G up there, or at least really close to it, not clashing with it. So what do? Well, several different things. One thing is don't play loud low notes. And that's a real thing, in some kinds of music. In fact, pianos are tuned differently depending on what they're going to play because of this problem, because there's no great solution here. But let's say you have to play the loud low notes and you have some mid-range notes you're going to play with it, either on the piano, the mid-range notes, or maybe you're playing with an orchestra, or who knows what you're doing. Well, with an orchestra, piano just has a hard time melding. If you're going to play loud low notes and you're playing with an orchestra, you better be the soloist. Otherwise, because you'll stand out. That might actually be useful, but it's not, it's not going to meld. Now, if you want to meld with an orchestra, because there's some places where piano is used, well, just make sure nobody else is playing, including the piano, when you play those loud low notes, and it's okay. You can deal with that. Or if they're going to play, they're going to play in those. They're going to play at those very low octaves. But in the end, there's a trade-off you do. And so, however you tune your piano, you would not tune it in perfect octaves. If you're playing with a string quartet, it would be closer to perfect octaves, and you just never play loud low notes. See, because the quieter you play those low notes, you still have stretches, but less. And you just don't, the music is written to take this into account. And, if you drive on ice, you just don't accelerate fast, unless you're a clueless student. But you just don't try that, right? You know that's not going to work, so you stay away from it, and that's what the composer or arranger will do. But if you are going to play low loud notes and mid-range notes, this is not a very strong stretch. There's even more stretching than this. But look how much the stretch is. Like you're talking about up 30 cents. I mean, that's a third of a half step. That's enormously out of tune. But what you do is for very low notes, you tune them flat. And then as you go up, in the mid-range, you keep them about where they're at, because that's a place where, like, say you're playing with other instruments, you're going to often play in the mid-range. And you want to be tuned about the same, for the fundamentals and for the first few harmonics as the other instruments. And then you go up. But this trade-off is messy because of this nonlinearity and because it depends on how loud you're playing. So it really, really depends on what happens. But the big deal here is when you play very low notes, if you're going to play loud low notes and notes in the mid-range on the piano, or maybe other notes, other instruments have mid-range on, if you tune the low notes flat, right, by the time you get, however much they're flat, say they're, you tuned it, I don't know what, 1 hertz flat, just for a number. Well, by the 12th harmonics, right, that makes 12 hertz of difference, right? So then the 12th harmonic is 12 hertz less sharp than it would have been, which it might be enough. It's sort of a trade-off. So you sort of figure out, well, about how loud are you going to play down there, about how much stretch you're doing, what other instruments you're playing with, and all those things, and then you tune it. People sort of wonder, why is it that really good piano tuners, it'll cost thousands of dollars to have a really good piano tuner do your piano. Well, it's because, they really know these things and they're really familiar with it. You can also buy your own tuning app where it just sort of makes you, gives you something to do, and it's certainly better than it being way out of tune. But this is, there's actually a lot of know-how in this. A really great pianist will have the piano tuned as it is tuned, for a concert, however they're going to tune it, and then practice on it for a couple of weeks in that hall. They've practiced their piano concerto for years, but at the very end they play on that piano in that hall if they want it to be really good. Have the tuning adjusted the way they need it. All right, so stretch tuning makes sense. We good? Yes?
So for the higher notes on a piano, why are they flat compared to, or I guess, are they flat for like... they're tuned flat compared to others, and it's just a trade-off. You really want the middle range to be about right. I'm sorry, they're tuned sharp. They don't go flat.
it's again the same thing. What happens if you're doing the thing where you're playing very low notes and very high notes on the piano together? You want them to sound okay. So if you're doing that by tuning this one flat, but not as flat as you really need for that, and tuning this one sharp to make up for the fact that you didn't tune the lows that flat, it works out. And the reason you do that is because most of the time you actually have mid-range notes. And that's the most important thing. You want to have these low notes sound okay with mid-range notes. So so it's a weird trade-off. And this curve, this is just a curve. There's actually, the details are actually quite different. And a professional person doing this kind of tuning that's really good at it, they use technology, but they also do a lot of listening. And they listen to the person play. They know the pieces of music well enough to know what kind of tuning works for it. They know, the manufacturers of the strings and all these other issues. There's lots of issues about pianos, right? Because for many of the pitches, you have multiple strings. And then how much do you detune those strings from each other to get whatever effect you want? There's lots and lots of issues. All right. But it is a weird instrument. It's one of the very few instruments I know of where octaves aren't a factor of 2. And it's one of the most common instruments. Still, if you look around the world, the biggest instruments by a large margin, if you don't count voice, is acoustic guitar and acoustic piano. So it's pretty amazing that our most common instruments have such odd characteristics. Okay, so now for the rest of today's lecture, I just want to talk about tuning and scales. Again, this is another thing that people do PhD theses on, and it's going to be a subpart of a lecture. This is from the ECE notes that we have, but the equal tempered scale. So again, to review, you have 100 cents per semitone, right? Cents is that's how it's defined. On the equal tempered scale, 1 cent is 100th of a semitone. Then you have this nice word here, enharmonic equivalence. What does enharmonic mean? Well, F sharp and G flat are the same. Now I'm going to point this out now because it's until last semester I didn't even notice this because I've been around these words too long. But there's 2 different words I use in this lecture that are unrelated. One is enharmonic and the other one is inharmonic. So these things up here are inharmonic because they're not integer multiples of the fundamental. And that's one concept. There's lots of inharmonic things. Bells are inharmonic in a very different way than these are. There's lots of inharmonic things, but that just means they're not quasi-harmonic. They're not, multiples of fundamental, the various partials. So that's inharmonic with an I. Enharmonic with an E is this idea that you dumb things down such that F sharp and G flat are actually the same pitch. And that's what the equal tempered scale does. So an F sharp and a G flat and an E double sharp, it's all the same lever that you hit on a piano. Or I should say a MIDI keyboard. Pianos don't have to be equal tempered, so they're an animal to themselves. But on a MIDI keyboard, right, you have one thing, and that's called enharmonic equivalence. An F sharp and a G flat being the same. That's called an enharmonic equivalent. So in the equal tempered scale, what more about it? The 12 through to 2. Why do you see this so often? Well, remember, right? You go 2 to the power, and then it's divided by 12 because there's 12 equal tempered notes per octave. So the 12th root of 2 is if you have the frequency of one note and you want to go up a half step, you always multiply by the 12th root of 2. Which is nice and uniform, and 12th root of 2 is a darn weird number, but whatever. If you multiply by the 12th root of 2, you do that 12th time and you got up by a factor of 2. Right, and that just comes from this equation here where you have a division by 12. So if nn increases by 1, you're going up by a 12th root of 2. And it's approximately 6% in frequency. Now that's approximate. That's not good enough to do a lot of musical stuff, but as an engineer, it's useful to sort of know that number. So what about this equal tempered scale? I wrote on the side here, Pythagoras' nightmare. Yes, that's not something that Pythagoras would like. So Pythagoras is responsible for a lot of things. You know, the Pythagorean the triangle, right? You know that what is it? 2, 3, 4. Is that right? 4 plus 9. No. No. What's the Pythagorean triangle length? What's that? It's got to be 3, 4, 5. 2, 3, 4 didn't work. 3 is 9. 4 is 16. 5 is, yeah, 3, 4, 5 triangle. There we go. How embarrassing. But anyway, my brain is, I can't remember very many things. Yes, a 3, 4, 5 triangle where you got integer lengths on the sides. He was really into that. He was into perfection through music and mathematics was a religion that he was a leader of. So he was a pretty odd guy, a long time ago. Did some very smart things. He also did a lot of music research. In fact, the name organ comes, you know, from really means experiment or laboratory kind of thing, and that comes from way back then in Greek times. But anyway, so yes, he would not like this stuff. Why would he hate it so much? Well, an equal tempered scale is very simple in the sense that everything is spaced by a 12th root of 2, but you'll notice a 12th root of 2 is not like the 3, 4, 5 ratios, right? It's not integer ratios of anything. And in fact, in Pythagoras' time, he had one of his followers actually was able to prove that if you have a 1 and a 1 triangle, right, it's the square root of 2 on the other side, he was able to prove there are no integers, not even big integers, ratios that's equal to square root of 2. So that person got excommunicated, and history books say 10,000 bulls were offered to the gods and all that kind of stuff. Anyway, that was just heresy. And for a long time in mathematics after that, right, there was 2 branches. There was the people that believed in proofs and people that didn't. So it was a rough time there for a while. Nowadays it just seems silly, but back then, when things are new, all sorts of things happen. Okay, so equal tempered scale is simple and versatile. It's the same for any key. It doesn't matter if you're in C major or G major or D major or whatever. But all chords are always stringent. Okay, you always have competition harmonics. Now, I think one of the reasons why this scale made it is because you already have all these weird tuning problems in piano, and piano got to be a super important instrument because you can play loud and quiet on it. You can do all these other things, and it's always a little bit out of tune, but it's okay because it's just so cool in other ways, and it's just an incredible instrument. So I think another thing that went by the wayside, well, if you're willing to deal with a little bit out of tune, then you can do the equal tempered scale. And all of a sudden, you don't have to retune your piano because you're going to play in a different key, you know, because you're going to play a different piece of music. So that's really useful. In our culture, in the last 100 years or so, we've pretty much gone totally over to equal tempered. So let's talk about equal tempered. Here you have this little melody. You're starting on an F, this is the frequencies of these notes, and then this is the here. I'll put this up here. This here is just each note like this. The C here is 523.2 hertz. And you divide that by the F frequency. So that's 1.498 times the F frequency. This one is 1.682 times the F frequency, so on and so forth. And these numbers, if you look at these, yikes, you know, except for this F, which is a 1, a unison. These aren't small number ratios. They're some horrible thing. So why are small number ratios so important? Well, if you have a harmonic sound and you want you play a chord, then if many of the harmonics line up, if many of the partials are at very close frequencies, it'll sound nice. It'll sound smooth. You know, it won't sound stringent at all. Where if they're close but not close enough, then you get that stringent sound. And you can think of it in beats between the harmonics. You can think of lots of different things. But the fact is, if the harmonics aren't close enough, you get a stringent sound. If they're way up far apart, again, they don't interact. But if they're close but not close enough in frequency, then you get that stringent sound. Well, here, if you have, in these examples here, even in something like this, where you just have a single melody, keep in mind that there's some echoing in the room and all this other kind of stuff. So these weird ratios and stuff do actually affect the music, even if you're not purposely playing chords. You get the stringency between notes and transitions and that kind of stuff. Okay, so then there's delta P, which is just the same as delta note number. This is just how many half steps. And these are note number. These are in on the equal temperate scale. So this is sense, and sense is the same thing, just multiplied by 100. Okay? Good so far? So in just scales, they're all based on small number ratios, frequency ratios. So every note in the scale is a small number ratio times the frequency of the tonic, or times the root of the scale. Okay, and that's a really different thing than this. For instance, if you're in this thing here, if you have an F and then an F sharp, that's not a small number ratio. Not even a medium-sized number ratio. Or if you play, I don't know what, a minor third or something, they're not nice ratios, integer ratios. I'm going to play you an example of something. There are various kinds of music that really do need to pay attention to harmonic spacing, and where the chords you play and the notes you play and stuff are very carefully selected. The pitches are very carefully selected so that you don't for harmonic spacing. This is sort of a hit you over the head example. This is overtone singing. So what you're going to see in here now is this is Benedict Schlotte, who's did this in December 5 years ago, way northern Europe. It's been dark for a couple months, sitting in your basement doing music. Well, this is what one of them people does, and it's quite beautiful, I think. But so there's this overtone singing, and he had talked about it, and so I'd asked about, what about examples you might have, and he has this. He made this. So this is the continuum part you hear is playing very slowly, changing things, chords, and those are processed bell sounds. But again, with very careful attention to to pitches. And then he's singing. Now, what's interesting about the singing is that sometimes the pitch you hear is the fundamental, and we're going to see a spectrogram of the voice of the singing, so you can tell what's going on. So at some points, especially at the beginning, you're always going to hear the fundamental as the pitch you're hearing. But other times you'll notice, hey, it's a different partial. Sometimes second partial, sometimes all the way up to fifth or sixth partial that you're actually hearing. So you'll do weird things like the fundamental will go down in frequency, but the pitch will go up in frequency. I'll show you what I mean. But if you're doing something like this again, you got to be real sure that all of your notes that are playing along with it and such are in a just scale, in nice small number ratios. So like I'm just going to point it out again the first time. Oh, now I screwed up. I think it was right here. Here you hear this as a pitch, and then you hear this as a pitch. I think, if I'm in the right place and didn't screw this up. And then I will stop rudely interrupting. Just listen for those weird changes. So it's a longer composition, but you sort of get the idea, right? He's picking different harmonics, and this is by mouth shape. This isn't by any post-processing. There's many different varieties of overtone singing. It's actually kind of cool to look up. Sometimes, especially when you take them out of context, it sounds like two pitches are being played. Although when you hear it in a melody, you know, you're sort of primed for which one you're supposed to be hearing. But anyway, now singing like this, right, clearly everything else that supports it, all the other instruments playing, better be tuned and equal temperament, or the whole thing just doesn't work. Because here, these are multiples of the fundamental, and they have to be. Otherwise, yeah. Now the vertical scale here, as you can see, isn't linear in hertz, and that's why they're unequally spaced. But yeah, they're integer multiples of fundamental. We good? Okay, so there was an example. There's many other examples, of course, in American culture. Barbershop quartet's a big one, where people are very, very careful about exactly what pitches they're playing. So I'm going to talk about just tuning here. Now, I have to do a disclaimer here because there is maybe not quite the religious zeal of the good old days of Pythagoras, but there's still a lot of people that very seriously work in these scales, and then I've once had such a student in this class who was very much into this and was very knowledgeable, and there's many different things people call the just scale and the Pythagorean scale. So I'm going to call this the Pythagorean scale with a disclaimer that, yes, there's some disagreement about it, but we're just picking one scale. There's many, thousands, literally thousands of variations, and with all sorts of different names made by all sorts of different people for different purposes. You'll see why. It turns out that, you know, I can complain about enharmonics and the 12th root of 2, but as soon as you go to small number ratios, it's not all just mom and apple pie. All of a sudden, you're inviting in a new set of problems. So, in here, you know, if you have linear harmonic spacing, stringent versus smooth intervals, we talked about that, just scale ratios. Okay, so I'm going to go through these things. I played an overtone singing thing, and you know, you can hear that, at least in that kind of music, you have to be very careful about what you're doing. Terminology, tonic here just means the root of the key, the C. So what we're going to do is do a C scale here. And it turns out, I can tell you, spoiler, in advance, that it used to be like if you look at older keyboards, you know, harpsichords and Pianos would be too expensive to do this way, but there were several manuals, right? 2 or 3 manuals. And why was that? That's so you could tune sets of strings to different keys and play different pieces of music during the same concert. Or maybe even modulate into other keys by switching between manuals. So a manual is just a keyboard, and they used to be tuned in different keys for a performance. Okay, so what is going on here? Here you have C, D, E, F, G, A, B, C. We have pitch class, which is one of those words that you should probably know. It just means basically half-step number within the octave. 2, 4, 5, and since this is major, you can see here there's E and F as a half step, and B and C as a half step. Then sense. That's just the same thing multiplied by 100. I keep doing the sense thing because people that work in tuning do work in sense. And even people that really don't like equal temperament usually use it as a meter stick. So, they're using it as, you're saying deviation from equal temperament very, very often. So many cents flat, so many cents sharp. And even in the continuum, when you turn on the on-screen display, right, it's showing you equal temperament when those lines are vertical. You don't have to play that. You can play whatever you want. If you turn off the rounding options, it's really free tuning, but it's still a reference. It's still useful to know. So as people experience with this know that, oh, they want the flat fifth, or they want this, or they want that for a particular place. And so it's useful to, and especially when you're studying it. So now this is a just scale. And this is, I drew a darker line there. I will, by the way, give you this chart. I'll let you take a picture of it after lecture, but the other thing is I will give you this chart if you need it on an exam. So don't, you don't even have to put it in a cheat sheet unless you want to. What is this just scale ratio? Well, this is what defines this just scale, which I'm calling the Pythagorean scale, with the caveat that maybe that's not what everybody else calls it. Hard to agree on anything. So what is the ratio? Well, this is a frequency ratio. So 1/1 means that's the ratio to the tonic. Okay, the tonic is C, and this is the C, so that frequency ratio, and I'm not even giving it hertz here, because you might have a just scale where especially over history, how people tuned their instrument and what it actually meant to have a middle C or a middle A. A440 is drifted around a lot. Sometimes it was sharper. For much of history, it was flatter than what we use now. So your higher or lower frequencies. But whatever frequency you're using for your C, there's a 1-to-1 ratio, well, between it and itself, and a 2-to-1 ratio for the C above an octave above. Erase that piano thing with stretch tuning out of your mind. That was a very weird special case. We're no longer talking about that. So in any normal situation, an octave is a factor of 2, and in fact, when you're studying these tunings, you always just ignore what octaves things are in. We don't care about that. So 2-to-1 or 1-to-1 is exactly the same. You just divide that out. Now, when you look at the G, which is a fifth, this is a small number ratio, 3-to-2. Okay? That's what a perfect fifth is. So what does that mean? That means, well, if you play a C and a G together, the C is going to go through 2 periods, that's the denominator here, while the G, the numerator, goes through 3 periods. Right? If the frequency ratio is 3-to-2 in hertz, that's what's going to happen. 3 periods of the G for every 2 periods of the C. And overall, that repeats. Right? You'll always have every 2 periods of the C. You have a very nice and stable waveform that way. Now, nothing in nature is totally stable, but if you did it on a synthesizer, you would see something where it would, you'd see exact matches. Are we good? So that's what 3-to-2 means. I just wrote these little numbers in circles here. That's just for me, so I can go through these in the right order. You don't have to, you can ignore those. 4/3. Okay, so here's the fourth, and that's 4/3. Again, small number ratio, and then the third here is 5/4. Okay, so these are all nice small numbers. They get a little bit 5/3 again, 5 periods of A over 3. That was pretty nice. Now, there are some that are more stringent, right? The bigger these numbers get, the more stringent it gets. If they're not even integers, then, well, all bets are off. So we're not talking about equal tempered right now. We're talking about this here. But here, 9/8 and 15/8 are pretty weird. But again, you want the B to, you want to have this thing where you build up tension and release it, right? So you want to be able to have stringent things. This is a lot less stringent than what you would have in your in an equal tempered scale, but whatever. It's still you still have that concept. You just don't have it all the time. We good? All right. So then let's look at this next line. This is using that equation for the equal tempered scale. Okay. This is just figuring out how many cents above that is this. And the equal tempered scale would be 200 cents. This one here is 204 cents. It's 4 cents off. Now, a spoiler, 3 cents is about the accuracy you need to sound in tune. You can hear much more accurately than that under various conditions. But, just for something to sound in tune to a trained musician, 3 cents is about good enough. Rule of thumb. Okay? So, 4 cents, that's pretty out of tune. But 386, man, this really should be 400 for... the equal tempered scale uses 400, where if you want the small number ratio, it should be 386. That's way out of tune. So if you play a C and an E together in equal tempered scale, man, that's way more stringent than it should be, in at least if you were using a just scale. Does that make sense? 498 here, that's pretty close. 702, that's pretty close. And this is actually one of the reasons the equal tempered scale works at all. This is one of the reasons we ended up with 12 equal tempered notes per octave. Because these two intervals are pretty darn good. Yes, 3/2 is not exactly 700 cents. It would be 702 cents. But, boy, that's close enough. And as I keep saying, in acoustic instruments, you always have a little variation anyway. So this isn't bad, as is the F. But the other one, the A is horrible, right? Again, this is way off from 900. That's like if you're playing scales for your instructor would tell you to go and practice some more. This is bad. 1088, again, is pretty far off, but, probably less harmful. There's a lot of different things people do with that B anyway. Who knows? But not great anyway. And then 1200 is the same as 1200 because it's just factor 2. Right? 1200 cents again. It's just 100 times 12 half steps. That. So it's really good to look at this. There are intervals here that really, to use a technical term, suck. And we're just so used to listening to them all the time. Okay. But they're just way off. And no musician that plays an instrument that can play in tune would play this way. It's just, oh my God, it's just way off. It's just a matter of convenience. It's like fast food at McDonald's, it's not bad. And there's and it's very convenient. And contrary to popular belief, it won't even make you insanely fat unless you eat too much of it. It has its place, but this is as if everything changed to McDonald's when everybody goes to equal temperament. Okay, so now we have this just scale ratio. I want to talk about this last because this is not very hard, but all this stuff is confusing, okay? Because there's all these stupid little small number ratios. What is this? All this is if I want to take the frequency of C and get to the next scale step, not the next half step. Remember, this is just scale. It doesn't have a C sharp. Does not exist, right? And just tuning, you are in a scale, and in an octave you have 7 notes. That's it. Period. You don't have the other notes. You're going to a different key if you have these other notes. So there's only 7 of them. In a major scale, right, they're this spacing and half steps, but that's about it. So now what is this telling you? This is telling you if you're going from C to D, you multiply the frequency by 9/8. And then from D to E is also a whole step, right, just like C to D is, but the ratio is different. It's 10/9. And here's where we're starting to figure out, uh-oh, this doesn't look so good. You know, I mean, it's okay. You know, these ratios are nice. It sounds good. But you can see how you're going to start getting a lot of problems here because these two are both whole steps, but they're actually a different frequency ratio. Right? So this is C to D. This is D to E. How did I get D to E? I just took 5/4 divided by 9/8. There's nothing magic here. Right, so this is not higher math. Then we have 16/15. Well, that's a half step. That's okay. Now we have 9/8 again. That's a whole step, and it's similar to the other whole step. 10/9 again. G to A. We have another whole step, and then we have 9/8 here. A to B, another whole step. So we've got 2 different whole steps, and then here's our half step, 16/15. At least there's only one kind of half step. Now, you can do different ratios, these original just scale ratios. You can use different whole number ratios and have different trade-offs down here. You know, and actually the frequencies between half steps don't even matter that much. Normally that's not what you care about. Normally what you care about is this line up here. You know, that's in that key, when you play chords, this is how, you know, this is how smooth they'll sound, you know, how well the harmonics will line up. But this just scale ratio is really important if we want to generate other keys, and that's what's going to happen later. So just sort of keep in mind what it is. But the real thing that you wouldn't really give these numbers normally to define a scale. You'd normally give, hey, what's each note in the scale compared to its tonic? All right. Questions so far? So, this scale, which I call the Pythagorean scale, is pretty darn amazing. And if you hear people properly do this, it's actually quite impressive. Now, there's different kinds of microtonal music. There's microtonal keyboards, or people that, they usually have many, many pitches per octave, or even regular keyboards, MIDI keyboards, you could even tune them, right, into this scale. And then everything hits exactly on the scale. And that's okay, but it's still sort of antiseptic. Actually, what's most interesting to me is what happens when people are well-trained, hear these things, and play. And then that's sort of a different thing. They sort of do this, but you know what they're really doing is every pitch that's played, or every time they play a note, they're listening to everybody else and micro-adjust. So that's sort of a different thing than exactly following this. But anyway, if you exactly follow this, I mean, it is almost exactly following this, except there's variation in it. And there's a big difference when you're listening to music between something that's antiseptically perfectly anything and something that, you know, has some small variations where people are trying to play perfect, but they're not quite getting it. And, you know, the better people are, the better they are to perfect. But, you know, they're never quite there, and that's part of the beauty of it. So here's triad frequency ratios. So the major triads here in this are all perfect. Totally amazing. Now, there's few tuning systems where this happens. Usually you give up one of the major triads and say, well, you know, in this composition, I just won't use that major triad. Just leave it out. You know, it's like when you go to the doctor and you say, oh, it hurts when I do this. You know, and the doctor tells you, well, don't do that. You know, there's a solution to some problems. CEG frequency ratios. So what am I looking at here? 1 to 1 is the C, and then the E is 5 to 4, and then the G is 3 to 2. And then I put them under a common denominator and get 4, 5, 6. Right, 4 to 5 to 6. Everybody see what those numbers are? I'm a bit concerned about this because most of this course is conceptual, and you get kind of good at that, But in this case, I actually want you to be able to grind out really simple things if you need to on because I got to test something on the exam. So the FAC, I did the same thing. Is 4/3 is the F, 5/3 is the A, and 2 to 1 is the C, and that's 4, 5, 6. Now the 2 to the 1 is, yeah, I mean, basically, I'll just put these under a common denominator. And finally, GBD is 3/2, 15/8, and 9/8 by 2. You don't care what octave it's in, and this is just to get, so the by 2 is just so you end up with a nice common denominator, 4, 5, 6, or integers, 4, 5, 6 again, those frequency ratios. You can always switch octaves on anything if you want to. So basically, what happened with the GBD is that you did G, B, and then next octave up D, and that's why I have a multiplied by 2. So those are the major triads. If you forgotten or never knew what a major triad was and a minor triad, it just depends if the two whole steps are before the middle note or after the middle note of the triad. Anyway, ask your friends. It's something you should know before you're in this class. But they're important. Triads are important. They sort of reflect on what kinds of things you can do that sound stringent or less stringent in your music. Now, let's do the minor triads. EGB, same kind of process. You got 10 to 12 to 15. Just put them under common denominator so that you just have the integer ratios, right? So what do these things mean when I say 10 to 12 to 15? It means 10 periods of the E will complete in the time that 12 periods of the G complete in the time that 15 periods of the B complete. Right? So on an oscilloscope, you get a very stable picture. Well, if you trigger at the right times. If you know how to trigger your oscilloscope well. Yeah, you get a very stable picture. And again, minor triads, you can tell they're more stringent than the major ones because look, 4, 5, 6 versus 10, 12, 15. Right? The bigger numbers. The bigger the numbers, the more harmonics you'll have that are close, but not so close that they sound smooth. What happens here, though, is ACE is also 10, 12, 15, and as an exercise, just for something to do when you're studying for the exam to make sure you understand this, figure out what the DFA is. It's disgusting. It's a huge mess. So what happens here is you have this tuning where everything is just perfect. Perfect triads means, for minor means 4, 5, 6, for major, for major means 4, 5, 6, for minor means 10, 12, 15 ratios, and then you have one that you just stay away from. So it's totally disgusting. One of the reasons that there's so many different tunings and variations of this is that people try to even that out some. What if you actually want to use all the minor triads in your composition? Well, at that point, you use a different tuning so that you don't have the sore thumb that shows itself every once in a while. And you try to make maybe larger number ratios in more places, but no insane ones. So and lots and lots of variations there. Are we good? All right. So this is another confusing topic, but I think important. Can we use a keyboard to play both a just C scale and a just G scale? And the answer is no. One keyboard doesn't do it. And you have to know why, and you want to be able to compute the frequencies of notes. So what are we saying here? So say you have a C, a keyboard, you've tuned it in C using that scale above. Now you want to play something in the key of G. What are the problems you're going to run into? You'll see it right away here. What we're doing here, and this is the confusing part, why are we starting with G equals 3/2? Well, what we're starting with is this C thing here. The G here, which is a tonic of this new scale, but on the original C scale, which is what our keyboard is tuned to, it's 3/2, right? And so what we're going to do is just look, hey, in the G scale, if we have it go back to C, reference it to C, where do we run into trouble? Well, so we start with 3/2, and then we do the very first scale step here is 9/8. So C to D, from the tonic to the whole step up, is 9/8. Well, we do the same thing here. We take our 3/2, multiply by 9/8, and we get 27/16. And you will note above, there is no 27/16 in that diagram. In that, right? There's no 27/16 anywhere here. So what does that mean? Well, that means that the A, you can't play it in something where the A is tuned for the C scale. The A is something different. Right? The A in the C scale, if you look up, there's 5/3, and here's 27/16. 5/3 and 27/16 aren't equal. So, yeah, this A is different. Now, as we go on then, take this 27/16 to multiply up the next scale ratio to go up the next whole step. You've got 10/9, then you get 15/8. And 15/8 is exactly the same number that you see in the scale above, and all the rest of them are the same. So it's really only this A where you end up with this weird nastiness. Except you also get an F sharp. Now, F sharp is okay. It's a black key. You didn't have a black key that you used in the C scale. So F sharp's okay. You got this key you weren't using before. You use that. So the F sharp is a new note, and it's a new number that you didn't have in the C scale, but that's okay. The F sharp is... so really, in the C scale and the G scale, if you compare them, the G scale, which is the neighboring scale in circle of fifths, there's two new pitches. One of them is F sharp, which is harmless because you haven't used that black key, but then you also have a different A, which is far from harmless because you already assigned a frequency to the A key. Does this make sense? All right. When I took this class, at this point I was comatose, and I actually didn't understand the first time. So if you don't understand, just ask something. I will also leave this out for you to take pictures of. But yes. And this stuff seems sort of fiddly, but it's like doing the nitty-gritty of MIDI, as I said the other time. It's important to understand these details, to have an idea of what's going on, and why is equal temperament not so good, but why are alternatives a mess too? And why would people still deal with alternatives despite the fact that it's a mess? Are we good? Okay. I'll just wait until everybody is done. Have any of you listened to the audio? I guess you're here, so you probably don't do that, right? Because, people out there are saying, yeah, but I can never be painful, but or painful, or not even painful. Cool. Yes, they are recorded. And in fact, if it's problematic for you to get them from Echo 360, they remove them after some time or something, or I don't know if they let you look at them. Anyway, I do eventually put them on YouTube also. So I'll try to do that for all of them. So worst case, dig around. I think it's under, I don't know what they're under. I don't know what my channel is called. I don't know enough about YouTube. I just made a channel. So it always says Lippold Haken there. So I assume that's what the channel is called to. But anyway, if you look for ECE402 lectures or something, it should find them. I didn't put all the fancy tags on them and stuff because I didn't. And I can't monetize them, but boy, if you want to watch this, I'm not going to make you also watch ads, so you're safe. Because there's copyrighted material. And only one of the examples so far, the copyright holders were so ambitious that they made me cut it out. But so there's, some sound examples aren't in there. The sound examples aren't that great. There's other copies of them elsewhere. You can look for them if there's one you're interested in. Or download the thing I have for them. Okay, so very good. So now I want to talk about a few more issues here. The first one or not issues, but define a few more things, because these are things that you should know about also. And again, even if you don't do this stuff, I mean, I don't really do this stuff, but it's good to know about it. And if you've seen it before, well, that's okay, then enjoy it, that it's easy. There's many different kinds of commas. So what's a comma? I used to call them kludge factors, but somebody objected to that and thought it wasn't respectful. So they're tuning errors. So commas are small intervals, and in fact there's notation systems in which the commas are actually notated. Like you have sharps and flats, you can also have many other symbols notate how much sharp and how much flat do you want, rather than just assuming that the person will figure it out. Or maybe really want people to sing a very particular pitch. And some singers or some players can actually do that. So what is the syntonic comma? Well, it's the error between the two just scales. I just told you the A was different. Between the C scale and the G scale. And those are neighboring scales, right? And they're different by a factor of 81 over 80 if you take those ratios that we had on the previous page. That's 1.0125. First glance, hey, that doesn't look bad. That's a terrible error. Remember that, first of all, you can hear easily over 8 octaves in frequency, and it's your most accurate sense that humans have. So, man, that's terrible. Here, if you look at derived from the equal tempered scale, this isn't really a new formula, but if you want to figure out what is this, what in cents is the frequency ratio here, it would be 21.5 cents. If this derivation for you isn't instantly obvious, that's okay, but look at it on your own or when you're studying. It makes sense to figure this out, right? It's not science, but on the other hand, it's frustrating in a lot of music stuff because you have a couple of subtracts and adds and maybe even an exponential, and then, the formulas are all simple compared to what electrical engineers are used to, but it's still easy to get confused. So LG here means log base 2, by the way. Okay, so ln is natural log, LG is log base 2, and log is log base 10. And that's true for all of this course and much of engineering. Okay, so that's 21.5 cents. That's really big. Remember, 3 cents is what would be in tune. You can hear better than 3 cents in some situations, as I said before, but, if you're just playing notes and stuff in a normal situation, people would say 3 cents is in tune. 21.5 cents, that's almost, that's like a fifth of a half step. That's like very big error. Noticeably out of tune, quite disgusting. So your A will be quite out of tune if you're trying to play in G when your keyboard is tuned to C. That's all that says. Is that good? And again, we use cents. Why? As a scale. It's not because we're married to equal temperament. It's just you need some sort of meter stick, and that's what this is. So let's talk, then that's one comma. I'm only going to talk about 2 of them. There's hundreds of them defined, probably 50 or so that are in common use. I'm going to tell you 2 of them. So here's the second one, a Pythagorean comma. And in music theory, we talk about a circle of fifths, but, if you look at these tuning scales, it's more like a spiral of fifths. Why is it not a circle of fifths? Well, actually, there's also the line of fifths, which is mentioned in the homework article you're reading. It's all okay. An equal temperament, if you keep going up a fifth, like say you start on a C, and you keep going up a fifth on your keyboard, and your keyboard's long enough, eventually you end up on the C again. Right? Because, you start from C and you're going to hit G, and then you're going to hit D and A and E and B. You're going to keep going up, but eventually you'll hit all the black keys too, and you'll end up on C eventually again. Okay, so that's why it's called the circle of fifths, because you end up at the same place. Maybe many different octaves off, but you'll end up at the same place. If you ignore octaves, it's same place. Okay, so what is this funny formula here? 3/2, that's a ratio for a fifth. That's a perfect fifth. And I know of no scale that ignores that. I was saying, there's many, many different scales. 3/2 is always a fifth. That's really fundamental, just like 2 is always an octave, or 2 to 1 is always an octave. So 3/2 is a fifth. Now you're going to go up in order to hit every. If you want to get back to a C again, say you start on a C, you want to get back to a C, you have to do that 12 times. You have to go up a fifth 12 times, and you'll end up on your C. 12 is the number of half steps in an octave. 12 is also, number of times you have to go up a fifth until you land on C again. Does that make sense? By the time you've done that, you're also going to be way, high up in your octaves. So that's what the 2 to the 7th is. All that is dividing out. You're 7 octaves up, and you don't care. You want to get rid of the octave difference. So 2 to the 7th is just putting you back in the original octave. So by the time you've gotten back to the C, you're at a C 7 octaves up. You divide by 2 to the 7th. And then just reducing these things, you end up with 1.0136 is that ratio. We had 1.0125. 1.0136, an engineer would say, it looks about the same. Remember, again, pitch is the most accurate thing you have. And even the 3 cents rule, that's only true if you aren't sustaining chords. But if you're sustaining more than one note at a time, you hear beat frequencies between those and stuff, right? So you can get way, way higher accuracy than 3 cents. Even if you're playing, a 4,000 hertz note, it'll, and if you go up to 4,000 and a half hertz and you play that with a 4,000 hertz note, well, you get 2 beats a second. And even though that's a tiny pitch difference, and you wouldn't even be able to hear it if you had just played one note or the other one. You wouldn't know they're different. But when you play them both at the same time, you certainly hear the beats, right? Because they're constructive and destructive interference. So, these numbers do matter. It turns out that this one here is 23.5 cents instead of 21.5, and it's a Pythagorean comma. That's cool. So what this this happens to be this enharmonic, now in this case written with an E, not the enharmonic with an I that I was talking about before. Enharmonic with an I, again, means, hey, your partials aren't integer multiples, not even close to integer multiples of the fundamental. Enharmonic is a different thing. That's like the B flat and the A sharp, which you, in equal temperament anyway, say are the same note. But actually, they're equal in temperament, but they differ by 23.5 cents in just tuning, which is a big amount. And the only reason we put up with this is convenience. Don't have to retune your instrument every time. Okay? So this enharmonic number, this is the way I like to derive it here from the circle of fifths, because that's really fundamental in music. But it turns out that B sharp and C, or C sharp and D flat, all those enharmonic things, which in equal temperament we say are the same, they actually differ by 23.5 cents, or by a Pythagorean comma. All right? So enough about tuning. This is just an intro to it. If you ever run into somebody who's really into tuning, it's a subject quite close to people's hearts. And it's like in Germany, in Germany it's kind of funny. They have quite a few car accidents because, well, they got like no speed limit on the Autobahn in many sections and stuff. But there's this idea that, the symbol of freedom, in the U.S. it might be guns, but in Germany it's not having a speed limit. And people just, we live in a free country, there shouldn't be a speed limit. That seems foreign to us, but so does our idea of freedom. Anyway, for people that are into tunings, it's a really big deal. And to just poo-poo what they're so attached to is a mistake that you will learn if you meet somebody who is really into it. And there really is something that the rest of us are missing. If you haven't, trained yourself to hear these things, it's just, you don't notice. It's like not being able to appreciate poetry, or not being able to appreciate a beautiful scene in nature or something. You really are missing out in life. So that I will give them. Okay, so now we have just we're going to end here. We have smallest perceptible pitch difference. This is called delta F, J, and D, just noticeable difference. And so this is important for pure tones, for sine waves. It's 2 to 3 hertz between 62 and 1,000 hertz. And above 1,000 hertz, it's 0.3 to 0.5% of frequency. This is extremely important. Do not forget, this is extremely important. This is for pure sine waves. And if you actually look at this more, unfortunately, I talked too long, I'm running out of time here. When you look at this more carefully, if you go to lower notes, this is huge. This number here, 2 to 3 hertz, is just enormous. It's like, you know, at the very low end of a piano, it's like more than a half step. But pianos don't play sine waves. The reason that you hear it so accurately is that you hear, you know, easily 100 harmonics on the piano. Your ear is aggregating all of those and figuring out what the fundamental is. And any small variation in the fundamental that you couldn't even hear at all, in the 100th harmonic, it's 100 times as big. So that's how you get that super accurate pitch, is from the harmonics. So the sine waves are nice. These are true facts, and don't misuse them. Because you have to look at all the sine waves in your... So you have a tiny little variation in your fundamental. That tiny little variation is 10 times as big in the 10th harmonic, 100 times as big in the 100th harmonic. And that's why you can hear so accurately. There's a rule of thumb here for phase oscillators. I like to say 3 cents or 0.05 hertz, whichever is smaller, depending what pitch range you want. Why do I say 0.05 hertz? Again, because you can hear beats. 0.05 hertz, that's a 20-second period of beats, right? 50 millihertz is 20 seconds. That's a long time. And, you know, if you're hearing 20 or 21 seconds, that's a pretty slow beat. But in synthesizers, you got to be careful because people do weird things. You know, what if they take that beat rate and they control pitch with it or something? You know, people do patch it up any way they want. So if you want to make a general good oscillator, you know, do 24 bits like I showed you, and you'll be safe. But anyway, here's sort of where I came up with that. And it's because if you're just listening, this 0.05 hertz is really overly accurate. But if it's being used in special ways, like as a low-frequency oscillator to control something, it's really, really good to have the accuracy. Remember, your phase oscillator might be used like an envelope. Who knows what people are going to do with it? You don't know. Okay. Sorry I went over. I'll let you go. And I'll put these up here for you to copy if you would like to take a picture. I mean... You can do both sides. You can photo reduce it. You're not allowed to bring a microscope to read it. But yeah, and actually I really don't want to minimize making the cheat sheet because, frankly, exams are sort of a waste of time. I'm old enough they won't fire me for that. But, you know, it's such a silly way to stress people out. It's required, though, and I will do it. But, yeah. And I would like you to work on it. I'll give you time off from the other things, like not have lab for a week, not have homework and such, so that, you know, if you spend 8 hours on it, you're still within our rules of what a course is supposed to be for 3 hours. I don't mean to take over your life. If you need more light, I can turn on that one, or is that okay with your... Okay.
Thank you.
We'll see you. Thanks.